Solar cells, much like those on a handheld calculator, would likely be used to generate the power on an SSP satellite by converting sunlight to electricity. However, power generation in space for an SSP system poses multiple challenges. First, an extraordinarily large area of solar arrays will be required for large-scale power generation. In addition, to hold down SSP system weight, solar array voltages much higher than any that have ever flown before may be needed. NASA and its partners are developing several different innovative technologies to meet this challenge. This is a key strategy. By pursuing several competing technologies in critical areas such as power generation, we dramatically increase our overall probability of success. Some of the technologies that you're about to see have the added advantage that they might be combined with one another, boosting power levels still further.
One path NASA is taking in its mission to develop efficient solar cells for space solar power is to create thin-film solar cells. Thinner and lighter than traditional silicon solar cells, thin-film solar cells require less material, as well as a lower-grade material. Therefore, thin-film cells are less expensive to produce. However, these cells have a complex structure, and high-quality cells are difficult to manufacture. NASA, in collaboration with the Ohio Aerospace Institute and Cleveland State University, has created a series of single-source precursor molecules. A single-source precursor molecule is a single molecule that contains all of the individual elements that are deposited on the final solar cell material. In this case, copper, indium, and sulfur or selenium are present in each single-source precursor molecule. The molecule is then grown onto the final, lightweight, space-qualified material. This simplifies the manufacturing process.
We've successfully produced a family of new compounds that can serve as single molecule precursors to a series of thin-film solar cell materials. The deposition processes that we've developed using these molecules can be done at lower temperatures to enable the use of lightweight, space-qualified substrate materials such as Kapton. Also, other workers have shown that these thin-film absorbent materials can withstand the rigors of the space environment.
To simplify the process further, NASA also developed a unique chemical process known as low-temperature chemical vapor deposition. In this process, single-source precursor molecules are sprayed as a fine mist into a chamber containing a lightweight, space-qualified material. Once in contact with the material, the molecules in the mist decompose at low temperatures, in fact, several hundred degrees Celsius lower than conventional processing. Once the molecules decompose, the molecules and the material become an absorber layer, or a layer of material that absorbs sunlight and converts that light into electricity. The absorber layers are then turned into thin-film solar cells.
What we've done is we've taken a chemically based approach. This enables molecular level or atomic level mixing of the elements. Because of this, we can do our deposition processes at much lower temperature. In fact, several hundred degrees lower in temperature. This enables us to do use much lighter, low-cost substrates, and consequently, it's a much lower-cost process.
To make thin-film solar cells truly practical for space solar power, NASA must continue to fine-tune its process for creating thin-film cells.
Well, the next step is to make more efficient cells. We also need to scale up our process so that we can deposit our solar cell materials on much larger substrate areas. Of course, space solar power requires extremely large areas, and we need to make a more manufacturable process to enable the use of larger equipment using a process that is much more reproducible.
Thin-film solar cells offer tremendous promise for space solar power by creating more efficient, lightweight, and cost-effective solar cells. However, this research can also benefit us in other ways.
There are many power materials that can be made using our process. Batteries, capacitors, fuel cells, and integrated electronics can all be produced using a chemically based process. Our chemically based process will allow us to do the depositions at lower temperatures using lower cost substrates and give us lighter electronics. And all of these benefits will improve our everyday lives.
Space solar power will require lightweight, high-efficiency, low-cost solar cells for power generation. Conventional solar cells have the potential to be 12 to 30% efficient in converting light to electricity, depending on the type of cell. However, when the new technology of utilizing quantum dots is incorporated into a solar cell structure, the cell's potential for converting light can increase dramatically.
Quantum dots are an extra layer of material within the solar cell structure that absorb the sunlight. They have the potential to double, possibly triple, solar cell efficiencies in converting sunlight to electricity.
First discovered in the early 1980s, quantum dots are basically a blob or group of atoms, and they are extremely small. In this image, a group of quantum dots are magnified to 4,000 times their original size. Without magnification, the dots measure 250 nanometers across. At 250 nanometers, approximately 20,000 of these dots could fit on Lincoln's face, on the front of a penny. Different sized dots absorb different types of light from the sun. While smaller dots absorb more blue light, larger dots absorb more red light. By controlling the manufacturing process, NASA can create quality dots that are the correct size. As a result, quantum dots have the potential to provide lightweight, low-cost, high-efficiency solar cells that are better adapted for the launch environment and have the ability to withstand radiation from the sun. Creating quality quantum dots that are the correct size proves to be a challenging task. NASA recently developed several different quantum dots for research, funded by the Space Solar Power Program.
We had to overcome quite a few obstacles to create the quantum dots. Our first problem was contaminants in the chemicals, which we had to then purify in order to synthesize the dots properly. Also, the size of the quantum dots is critical. Therefore, we needed to be able to create them in the appropriate size and isolate them so that we could eventually use them within a solar cell structure.
The next step for NASA is to create the solar cell structure in which the quantum dot can be tested.
We're at an exciting point in our research. We plan to develop a device structure in collaboration with the amorphous silicon group at Penn State University. We will build the actual quantum dot solar cell structure and test its efficiency. This will give us a comparison against the theoretical efficiencies of the quantum dot solar cell.
Solar array technology has made tremendous advances from the 10% efficient single crystal silicon solar cell to the 27% triple junction cell. However, many future NASA missions require power systems that must perform in harsh environments and at increased power densities. The Rainbow photovoltaic array concept offers the combination of high solar energy concentration and high efficiency power output. An experimental design of the Rainbow array concentrates incident solar radiation through a parabolic Fresnel-like prism array that spectrally splits the light and directs it onto an array of different band-gap solar cells that match the energy of the incident light. The actual concentrator consists of a lightweight thin film. Rigid array of prisms with solar cells selected to match the energy of the incident spectral bands. Band-gap matched solar cells were tested under the Rainbow produced by the prism array as a demonstration of the potential for high power output. The Rainbow concentrator uses prisms oriented on a cylindrical parabolic curve to spectrally split the incoming light and focus the resultant spectral bands on an image plane that supports the solar cell arrays. Modeling is used to determine the ray trace and focal point of the spectrum. A determination of the optimal prism type will maximize the power produced. Various prototypes of the Rainbow concept were examined, leading to the present successful prism concentrator solar array design. the efficiency of the system is expected to reach 40%. The rainbow array can be constructed in a modular form and expanded to handle the needs of a wide variety of space and planetary high-power needs. Each module, consisting of a prism concentrator and an array of solar cells, can be added to meet the future power requirements of a space solar power system.
Solar cells, much like those on a handheld calculator, would likely be used to generate the power on an SSP satellite by converting sunlight to electricity. However, power generation in space for an SSP system poses technologies that you're about to see have the added advantage that they might be combined with one another, boosting power levels still further. Multiple challenges. First, an extraordinarily large area of solar arrays will be required for large-scale power generation. In addition, to hold down SSP system weight, solar array voltages much higher than any that have ever flown before may be needed. NASA and its partners are developing several different innovative technologies to meet this challenge. This is a key strategy. By pursuing several competing technologies in critical areas such as power generation, we dramatically increase our overall probability of success.
One path NASA is taking in its mission to develop efficient solar cells for space solar power is to create thin-film solar cells. Thinner and lighter than traditional silicon solar cells,